Okay, welcome to today's webinar on understanding wireless LAN capacity in the CWNP monthly webinar series. So today we're going to be focusing on the importance of capacity. Last month we talked about coverage, and we'll be looking at application requirements, device requirements, and some general guidelines for gaining more capacity. It is an essential element of wireless LAN design, implementation, monitoring, and support with modern networks, because we're no longer in that era where we can simply say we'll install a few access points and people will have wireless access, because we're now running critical applications, or we're marketing that we provide wireless access at hotels and other hospitality areas, arenas, and things like this. And when you market that you're providing wireless access and then people connect to the wireless network and do not have effective wireless access to the internet, let's just say they get a little bit frustrated. So to avoid that, we have to make sure that we've designed for capacity, and that's what we'll be looking at today. Before we get into the specific topics of today's webinar, just a quick reminder of who CWNP is. We are a vendor-neutral wireless knowledge certification company. So we offer career certifications in enterprise Wi-Fi technologies ranging from the beginner level, CWTS, that's not mentioned here on this slide, all the way through to the expert level of the CWNE. And so for those that want to go through the professional tracks or the expert track, it begins with the CWNA, the Certified Wireless Network Administrator. This covers a lot of the areas of wireless and lays a solid foundation to help people understand wireless local area networks. And then we have professional level certifications focused on three specific and important areas: security, design, and analysis. Of course, the security area is going to focus on how we secure our wireless networks and prevent attacks and make sure our data is protected and private, and that access to our networks is only by authorized users or according to our policies and guidelines. And then the design focuses on the actual planning and design and implementation of wireless networks, and the analysis focuses on troubleshooting wireless networks. And then for those that choose to go beyond just those professional level certifications, we have the Certified Wireless Network Expert. Of those listed on the screen, it's the one certification that does not have an additional exam that you take, but rather you submit an application which is passed to the Board of Advisors for approval. All of the details of all of these certifications is available at cwnp.com in the certification section, so you can get more information there. Additionally, I just want to quickly remind you that we have the CWNP annual conference coming up in New Orleans. You can get more information at cwnp.com/NOLA. And for just a couple days left here, you can get a 10% discount by using the Wi-Fi Jazz registration code when you register. So if you haven't registered yet and you want to attend, make sure you do that. In addition to the conference, there are pre-conference training classes that you can attend as well. And so you'll want to look into that information again at cwnp.com/NOLA. Okay, so we're going to talk about capacity, and capacity I define is a subset of capability. So the thing that our users are after in relation to our wireless LANs is capability. That is the ability to do what they need to do. And in order for them to do that on an ongoing basis, we have to provide coverage, capacity, scale, and function. So coverage we talked about, as I said last month, and that's where you're making sure the wireless signal that you need is where you need it. Capacity says, let's go further than that and make sure that not only is there a wireless signal where we need it in the way we need it, but that we have enough APs providing the wireless coverage such that we also have the capacity that we need, and that those APs are implemented with a cell and channel plan structure that is going to give us the overall capacity that we require. Scale says we can grow as we need to grow the wireless LAN. So we have room for growth built in, and we have plans or methods that we can utilize to add more APs or in other ways scale the network to handle greater capacity. And of course, function is just what I need to do on the network. So for guests, this might be some kind of onboarding method. For our users, this is having the access they need to the applications that they need, functioning in the way they need to function. So it becomes partly an overlap with capacity and coverage, but in addition, it means having the network services available that allow them to do what they need to do. All of this comes under the umbrella of capability, so that's what we're after. Providing users with the capabilities they need will accomplish that through coverage, capacity, scale, and function. So our focus is on capacity, and really the first thing we have to do in order to provide capacity is define what we need. So we have to start by defining our application and device requirements. Applications drive requirements. Now that statement alone can be the end of the story to a certain extent, as we'll see when we talk about device requirements. And what I mean by that is that all devices are utilizing some kind of an application, and the way that application behaves is going to drive our requirements. Device capabilities are only part of the formula. So for example, if we look at the device pool that we have in our environment, such as laptops versus tablets versus mobile phones, and then specialty devices, the reality is that we can get caught up in looking at the maximum data rates those devices support. For example, how many spatial streams, channel widths, in 5 gigahertz, what channels do the devices support. We can look into all of that and talk about the hardware capabilities, and that's fine. We want to make sure we implement APs on channels that all of them support. But the reality is that on those devices, we're going to run applications. And those applications determine what we're actually going to need in relation to capacity on the network. Application vendors sometimes provide throughput requirement metrics, so they'll let you know that a user using our application with a certain % of busy time will demand X amount of throughput in megabits or kilobits per second. But when it's not provided, which is very common, we have to break it down into its component parts. And so we're going to look at the packet sizes, the packets per second, the % busy or the duty cycle of that application, and then the users that you expect to have per cell or per AP. Now, when the throughput demand is known, required data rates can be established. So whether we get this from the application vendor or we do it with our own calculations, only then can we determine the required data rates. In addition to this, we need to make sure we understand latency requirements. So it's not just about throughput. Some applications have, in addition, a latency requirement, particularly real-time applications like video conferencing and voice over IP. Things like streaming video and so forth, if it's not live, may support buffering to an extent that latency is not as much of an issue. But with live video streaming, even with some buffering that may be implemented there, latency becomes more of an issue. And of course, with voice over IP, latency is an issue. And latency is a factor of the delay in getting packets through your network. So how quickly can I push a packet from end to end through that network? For example, voice over IP, the common target is under 150 milliseconds to get a packet from one end to the other in a voice call. And in addition to that, there are things like variance in delay, jitter requirements, these kinds of things. So we have to make sure we understand those and factor them in to our communications. Because it's one thing to get a burst of throughput at some high rate, but it's another thing to be able to maintain that consistently over time with even lower packet sizes, which is typical of voice over IP, but having consistency in the communications at under 150 milliseconds for our end-to-end communications. So the throughput demand can be calculated by taking the packet size, multiplying it times the packets per second, and multiply that by the % busy times the users per cell. So for example, if my packet size is 1 kilobyte, to make it nice and simple, and I'm going to send out 2 packets per second, you might say that's 2 kilobytes. But the reality is I may only be busy 50% of the time, so I'm back down to 1 kilobyte. And then if I have 100 users in the cell, then I need 100 kilobytes per second. And so that is the way the formula can work to help you understand what you're going to need to drive through. And from there, you can extrapolate out to megabits per second and the actual kind of throughput you're going to have to provide in the cell. So it starts with application requirements, and it starts with understanding the different application combination that might exist on a device. So a dedicated device like a voice over IP handset may be dedicated to just doing voice over IP calls with possibly some extra communications used for notifications that might come through while on a call, things of that sort. But by and large, the majority focus is on getting a voice stream through. With a video camera, it's about sending the video across Wi-Fi, if it's a wireless client video camera, sending the video across Wi-Fi to some central server. And again, that's going to be something at 100% duty cycle probably, sending it all the time, but even if it's sending it all the time, what are the sizes of those packets, and it's dedicated to that application. But then you get to tablets and laptops, and now you've got a whole different ball game, right? Because you're dealing with varied applications running on that device. So you have to ask, what percentage of the time is the application being used? Is it a background application that does some work in the background, but when it's in the foreground, it's busier? These are factors that one has to consider. And there are some general estimations that you can utilize for many common laptop, desktop, tablet type applications. And I'll give you a reference to a tool that helps you at the end of this presentation with some of those. So then you have your device requirements. And here I'm talking specifically about specialty devices, not so much the requirements of the device in that a device can support 3-stream 802.11ac Wave 1 or something like that. What I'm talking about is specialty devices like wireless LAN cameras, voice over IP handsets, push-to-talk devices, door locks, and these kinds of things. It's important to remember that specialty devices are special applications. The same rules apply when calculating application requirements for wireless LANs because it's still an application running on that device. It's just the device is often dedicated to that application. So they're simply wireless LAN clients that run a dedicated and sometimes extra optional application. So again, a wireless LAN camera is fairly dedicated to what it does. Door locks are dedicated to what they do. Voice over IP handsets, push-to-talk devices, they might vary a bit with some kind of notification elements, something in addition to just being a voice device. They may have extra features and capabilities as well, particularly voice over IP handsets. Some of them are smarter devices that may also offer applications that run on them in addition to simply being a voice over IP phone, like email checking and things of that sort. So again, it goes back to knowing the application requirements so that we can jump from there to understanding the data rates we're going to need. Now we're going to get into that because application throughput requirements at layer 4 and above do not equal data rates. Data rates have to be higher than the throughput requirement. The reason is simply that we are going to lose overhead, and so lose to overhead. And so I'll talk a little bit more about that later. So when it comes to some general guidelines then, the first thing I always like to start with when talking about planning for wireless LAN requirements is to note what our tweet this says. It's rare to implement a very high density, or standard density wireless LAN. Most wireless LANs include areas requiring some combination in different areas. So in other words, it's not the most common kind of implementation where you say this is going to be a VHD implementation. Sure, you might say that for an area of the building. But the reality is if you look at a wireless LAN you're implementing in some type of an enterprise deployment, you might have a large conference hall where you go for presentations where hundreds of people go in for those presentations in the building. There you may need VHD or HD. But throughout the rest of the building, you may need HD or just SD. And so when you look at the building deployment as a whole, or the campus deployment as a whole, you're going to have a mixture of these. And so what you're going to find is that you have all of these different types of implementations that you may need in specific physical spaces within the deployment, and you have to make sure that you understand that. The last thing you want to do is implement the same standard density in the conference hall that you would have implemented in the office space areas. So it's important to keep in mind that you might have some varied implementation requirements. And when you're implementing for capacity, channel reuse becomes a big issue. It's about managing spectral efficiency, making sure you're using the spectrum that's available to you as efficiently as possible. The most challenging band that we use in wireless networking is the 2.4 gigahertz band, because we really, for most of the world, have 3 channels that we can use, 1, 6, and 11. There are some areas of the world where you can include channel 14, and you can go with something like a 1, 5, 9, and 14, or 1, 5, 9, and 13 channel plan, depending on the regulatory domain. But know when you're doing that, you are introducing some channel overlap. They're not considered to be non-overlapping channels, and so you have to manage that in relation to your overall capacity you're going to achieve by implementing such a channel plan. So when we have 3 channels, 1, 6, and 11, it becomes very challenging because you really need a minimum of 4 channels to truly do your channel reuse plan, or your staggered channel plan with multiple channel architecture, such that you have less co-channel interference. Therefore, in 2.4 gigahertz environments, you're going to end up with co-channel interference. And for those that might not know immediately what co-channel interference is, co-channel interference, or sometimes it's called co-channel contention, is just the interference that occurs because an 802.11 device has to listen for communicating 802.11 devices on the same channel. And if it detects them, it cannot talk. So as long as I detect another device communicating on the same channel, I can't talk. And that's true even if it's a different BSS, if it's not the AP that I'm connected to, but it's a different AP. If I can hear it, I still can't talk. So this playing nice results in co-channel contention, but what has traditionally been called co-channel interference. You'll see more of that in 2.4 gigahertz by far than in 5 gigahertz because any two APs both on channel 1 are very likely, even in a clean environment where you're implementing your own channel plan, to have some overlap, at the very least for the clients, and then also possibly for the APs being able to hear each other or see each other. So therefore, it's important that we separate them as much as we can, but understand that CCI is going to be a real issue in the 2.4 gigahertz space that's going to overall degrade your potential throughput. Of course, we also have other factors there that we have to be aware of in our environment, such as non-Wi-Fi devices and so forth. We'll talk about that more later. In the 5 gigahertz space, we have more channels. So in most of the world, you're going to have at least the lower 8 channels, 36 through 64, and then also 149 through 165 in many. In some parts of the world, you may or may not have these middle channels that are sometimes called DFS channels. Certainly 100 through 144 may or may not be available. And in some parts of the world, they may be the primary channels you end up using. The important thing is to know that you're always going to have at least 4 channels, more likely 8, 9, or even 12 or 13 channels that are available to you. So because we have so many channels in 5 gigahertz, and I'm talking about 20 megahertz channels, of course, it's going to be a lot easier to deploy our channel reuse plan so that we're not having our APs step on each other, but even more importantly, our clients, because we can have 2 or 3 channels of separation between our different cells. Now, that is within some level of constraints, because when we're doing higher density, even in 5 gigahertz, co-channel interference is going to go up. And we have to understand that even when we turn down the output power on the APs in 5 gigahertz, because we're doing higher density deployments in a space, there's still going to be co-channel interference because it's not just about the APs, it's also about the clients. And you can't, at least very often, turn down the output power on the clients like you can on the APs. So that becomes a big factor once you get below 20 to 25 milliwatts of output power. So when we're talking about channel reuse, then we're talking about these staggered channel plans, and the important factors to remember are your power settings. Too much power can be a real problem. So just because an AP can do 100 milliwatts of output power or more doesn't mean we want to. We probably want to keep that down at a more client-matched power level, somewhere under 50 milliwatts, possibly between 10 or 15 and 25 milliwatts in many deployments. And then there's the antenna selection, a strategy that you can use in order to try to prevent a cell from interfering with another cell in one direction, is to use directional antennas like patch or panel antennas, broadcasting toward the clients that should be part of that cell, and therefore having less energy going in the other direction where clients should not be part of that cell. In some cases, that kind of strategy can be useful, particularly in high density or very high density deployments. And then you have to remember that client transmissions are a real factor. So when you're dealing with your channels and you're thinking about the co-channel interference range, that range is greater than many people think because most people are just thinking about the AP and they don't realize the clients transmit too. Now, upstream data from the client to the AP is typically from 10 to 30% of the load, but specialty clients are an exception, like video devices, voice over IP phones, and door locks. However, keep in mind that door locks and voice over IP phones do not consume a lot of the airtime as individual devices because they send small packets, but they do send them frequently. And so they do end up consuming airtime that is spaced frequently, but they don't consume a large percentage of the airtime because they're sending smaller packets. It's still a factor that has to be considered, especially when you have multiple phones in a cell. But certainly laptops and tablets, when they kick into gear and start transferring a large file, checking email for the first time in a while, watching a streaming video online or anything like that, then they're going to start transmitting more data. But remember, a lot of what we do, if you check email, you're downloading email. If you download a file, well, you're downloading a file. If you're watching a streaming video, you're downloading the video. And so there'll be acknowledgments, possibly things like that going up from the client, but most of the data is downstream. Now, obviously, if you're uploading data from a client, it's a whole different ballgame, and now you could be generating more co-channel interference for other cells that can hear the client, but aren't necessarily impeded on by the AP to which that client is connected. So these are factors that we have to keep in mind, and certainly in 2.4 gigahertz, wireless LAN clients must be factored into channel reuse plans. And this is because, again, we only have the 3 channels, so a client at the edge of a BSS with its transmissions is far more likely to cause CCI with clients in other BSSs on the same channel. What we want to do then, as a general guideline for enhancing capacity, is drive clients to 5 gigahertz. Do everything you can to move as many clients as possible to 5 gigahertz APs. So with more channels in 5 gigahertz, it gives us a lot greater capacity, and we can enhance or accommodate greater capacity requirement demands because of this band. Now, there are several things we can do. You can use band steering. Now, this is a feature enabled on the AP where that the AP ignores initial 2.4 gigahertz probe requests and responds to 5 gigahertz probe requests from the same client in order to try to move them over to the 5 gigahertz band. You do have to monitor for orphan clients. There are some situations you can get into with band steering where clients do not steer well, and the AP needs to have some threshold to allow that client on. You can limit 2.4 gigahertz associations if the AP supports this, meaning you can go into the wireless LAN profile and control how many 2.4 gigahertz clients can associate. But once again, you have to be careful. For example, guest access, things like that, where you see a lot more 2.4 gigahertz clients because you can't control the device purchases. You have to make sure that you're obviously providing sufficient connectivity. And then you need to make sure you have sufficient 5 gigahertz coverage. So you've got to make sure the 5 gigahertz coverage that you need is there. Otherwise, the 5 gigahertz clients can't connect and they'll be going back over to 2.4 gigahertz. So a common mistake is to implement APs with 2.4 gigahertz and 5 gigahertz radios, enabling all the 2.4 gigahertz radios and creating similar cell sizes with 5 gigahertz as 2.4 gigahertz with power management operations. But then the problem is that you cannot implement as many 5 gigahertz APs because you're constraining the 2.4 gigahertz APs you can implement. So what do? Turn off the 2.4 gigahertz radio and have some APs that are just running the 5 gigahertz radio, or have APs that are 5 gigahertz only, which is of course harder to find. And then make sure you have properly configured clients. So many clients can be configured to prefer the 5 gigahertz band. They can be configured to use only the 5 gigahertz band, but that can be dangerous if they're clients that do leave your facility, simply because when you get out of the facility and they go to hotspots and things like that, there may simply not be a 5 gigahertz network to connect to, and so that client all of a sudden is unable to connect. So you have to be real careful with that, but you can certainly prefer the 5 gigahertz band. Does that work? Well, the answer is we don't really know for all devices. So there's a lot of secret sauce, hidden ways things work behind some of those toggles in client devices. And we're never really certain just how well they actually work or enhance connecting to 5 gigahertz unless we test ourselves. But enabling the feature is an important thing to do if indeed that feature is available in your clients. Now, another thing we want to make sure we're doing is utilize quality of service features. So what we want to do is take advantage of quality of service. Select clients that implement wireless multimedia WMM or QoS data frames when required for voice over IP phones and push to talk devices and these kinds of things. Make sure you're actually getting devices that support QoS. The vast majority of the newer devices, of course, do, but you want to make sure you're getting those. Ensure the APs, switches, and routers have QoS enabled and properly configured. So make sure that you're enabling this not just on the APs, but on all the devices in between. Ensure end-to-end QoS, in other words. It should not be assumed that QoS is already implemented on the wired network. It may be that you're dealing with a network that never really had a need for QoS in the past. It was a standard data network with a lot of email checking and file transfers and database server access and stuff like that, and not really any real-time applications until you get wireless, and then you get your wireless handsets. So make sure that QoS is implemented end-to-end, because just implementing it at the APs or controllers does not give you what you need to get those packets through the network with the priority that they demand. Yes, it's going to give you greater probability of getting the frame through on the wireless link in the speed that you need, but that does not automatically equate to getting it all the way through the network with the speed that you need. So ensure end-to-end QoS within that network deployment. Now also, here's a big one, and I like to state it in somewhat of a shocking way. Don't believe the data rate lie. Now, what I mean by that is APs are sold as being able to accomplish a particular data rate. It's often a very high data rate. The problem is that just because they are said to be able to achieve that data rate does not in any way mean that they actually can. And why is that? Well, it's because the client is the factor that determines the data rate they're going to connect at as far as the maximum capabilities. And even with a client, the maximum data rate capability of that client does not automatically mean that they are going to achieve that maximum client data rate. So let's talk through this. And I'll start with a summary statement that might be shocking to some. Even 802.11ac wireless LANs rarely see anything close to 1 gigabit per second in a BSS. So why is that? Well, first of all, AP maximum data rates are irrelevant to data rates you'll achieve in the real world. So let's assume all of your clients actually support the maximum data rate of the AP, which would be rare, but let's assume they do. They're still not going to connect with that data rate because they're not going to have the proper signal to be able to connect and transfer data at that data rate. So just because an AP can support some maximum data rate doesn't really provide any relevancy. As soon as you get today with 11AC 25 to 30 feet from the AP, certainly out of the room from the AP, you're already dropping well below the maximum data rate. So the reality is that that maximum data rate is simply not achieved by any significant percentage of your clients in many wireless LANs. Additionally, most clients will not support the AP maximum data rate in most wireless LANs. So where the AP might be a 3x3x3 11AC AP or even 4x4x4, the reality is that most of your clients will be 3x3x3 or lower, and most of them will be lower than 3x3. They'll be 2x2 or even just a single stream client. So they'll have fewer radio chains or spatial streams, and so therefore the maximum potential data rate they support will often be lower than the maximum potential data rate of the AP. In addition to that, they'll have insufficient SNR, signal-to-noise ratio, to achieve the highest data rates that they do support. And so if they are 30, 40, 50 feet from the AP, if they're on the other side of a wall from the AP, etc., they're going to be in situations where the signal has degraded enough that they're going to be dropping down with data rate shifting to some lower data rate. So the important thing, first of all, is to know that the maximum data rate the AP is marketed as is not anywhere close to the average data rate you're going to see in a cell. The average data rate you'll see in a cell is probably roughly somewhere half of that. It varies depending on the AP features, the client mix, and all of that, but the point is it's going to be somewhere well under that. Now you can see this by just going into any cell that you currently run and use a protocol analyzer that will report to you the data rates that the AP is sending data at. This can be a good picture. It's not necessarily an automatic reflection of the data rates clients are sending at, but you can go to the AP and you can see the frames that are going in and out of that AP and what data rates they're going at. ComView for Wi-Fi is a simple protocol analyzer that'll do this for you. So you can monitor on the channel and you can take a look at the frame data rates going through that channel. And what you will find is that on average they are far lower than the maximum data rate of the AP. So that's the first part of the equation. Don't believe the data rate lie. The second thing is that there's a bit of confusion that data rates equal throughput. But data rates do not equal throughput. Those are the data rates on the wireless link. So even if you get an average data rate of, say, somewhere around 200 megabits per second, the reality is that's not your throughput. Your throughput is going to be brought down lower because there are management frames and control frames. So these are things like your beacon frame going out from the AP that announce the features and capability of the AP, probe requests and probe response, association and authentication frames, reassociation frames, RTS, CTS frames, acknowledgement frames. These are all frames that are used to either manage access to the wireless network or control the communications on the wireless network. And so there are extra frames that are sent out. They're going to use up some of that time that's available, which will no longer be available for actual user application throughput. In addition, you have CCI and ACI. We've already talked about CCI, so even though I might be able to send a frame at, say, some very high data rate of 11N data rate, like 450 megabits per second, well, okay, I can send my frame at that rate, but I can't send a frame at that rate one right after the other continually, consistently. Even when you accommodate for the management and control overhead, I also have the fact that I've got to wait to send the frame. So I'm not going to get that throughput, even if you're calculating, though, the aggregate throughput in the BSS. Remember that other BSSs are also communicating on the same channel, very likely, causing co-channel interference. So within my BSS, the aggregate throughput will be lower for my BSS because of the times the stations in my BSS have to be quiet because of a frame they see from a different BSS. And then there's also adjacent channel interference, where you see this a lot in metropolitan areas, in shared buildings, where you've got people, particularly on 2.4 gigahertz, that don't know how to implement a wireless network, or they're using some kind of an automatic channel selection algorithm that's not configured right or doesn't work right. And so you see channel 5 and channel 7 and channel 9 and so forth being used, causing ACI, frame corruptions and retries from this, that kind of thing occurring. And then you've also got non-Wi-Fi. So you've got devices out there that are not Wi-Fi devices communicating on the same channel, even if it's a low duty cycle, because they don't play nice, they don't listen before they talk, they can cause interference with wireless LAN frames and cause, again, retries. So because of all of this, even with 802.11ac, even Wave 2 wireless LANs on 802.11ac, you rarely see anything close to 1 gigabit per second in a BSS today. And so when we're talking throughput as opposed to data rate, what we can actually achieve, that's the key factor for capacity, and that's what we have to keep in mind when we're designing a capacity plan. So here's the summary of it all that's very important. Wireless LAN design should be driven by quantified capacity requirements. In other words, we shouldn't just guess about what we need. We should calculate what we need and then build our wireless LAN around it while keeping in mind these issues we've talked about, like channel reuse, pushing to 5 gigahertz, making sure that we understand what throughput really is versus data rates, and all of the issues that can lower your throughput, like CCI, ACI, management overhead, non-Wi-Fi interferers, and so on. Now, as we're wrapping up this presentation, one thing I'd like to point out to you is an excellent tool provided by Revolution Wi-Fi, the Capacity Planner. You can find it at the URL listed here. This is an Excel spreadsheet. You can download it for free, and it's a great tool. Just a couple of tips when you're using it. You will see tabs for applications and for devices. You can go in and create your own custom devices, change the name to reflect your device, get the spec sheet from your vendor, and then you can put those custom devices in there. And then you also, on the applications tab or sheet, you can go in and create custom applications. So define your application requirements and then go in and define the custom values. Then you can go back to the main sheet for the capacity planner and actually use those custom devices that you have created in those custom applications. And this is a great tool to do some capacity planning analysis to figure out what you're going to need as far as number of APs and so forth to accomplish your wireless LAN capacity plans.